This video will cover radiation and the concept of half-life in radioactivity. We will cover radioactivity, the detection of ionizing radiation, sources of background radiation, and the definition and application of half-life. Radioactivity can be detected using a photographic film or a Geiger counter. Examples include a radiation badge containing film and a Geiger tube with its counter. Photographic film darkens when exposed to light and radiation. Only ionizing radiation can penetrate the badge, so darkening indicates a person has been exposed to radiation. In a Geiger tube, radiation produces ions in a low-pressure gas. The thin mica window allows alpha radiation to enter, while gamma and most beta radiation can enter through the metal tube's sides. The activity of a radioactive source is the number of decays per second, measured in becquerels, BQ. 1 becquerel is equal to 1 decay per second. Let's solve a question. A radioactive source undergoes 72,000 decays over a 10-minute period. What is its average activity in becquerels? To find the activity in becquerels, we calculate the decays per second. 72,000 decays over 10 minutes equals 72,000 divided by 600 seconds, resulting in an activity of 120 becquerel. Here is question 2. A radioactive source has an activity of 25 becquerels. How many decays would be expected over a 3-hour period? With an activity of 25 becquerels, that's 25 decays per second. Converting to hours, we find the number of decays in 3 hours is 270,000. Background radiation is low-level ionizing radiation produced all the time. Most of it occurs naturally, but a small amount comes from man-made sources, such as nuclear weapon testing. Radon gas, accounting for 50% of natural background radiation, seeps into buildings from the Earth's crust. Areas with granite rocks, like Cornwall, have higher levels of radon gas. Cosmic rays, produced by nuclear reactions in stars and supernovae, continually bombard the Earth. Our atmosphere protects us, but exposure is increased during jet travel. Internal radiation is background radiation from radioactive sources within our bodies, like carbon-14. Man-made sources like strontium-90 can also contribute to internal radiation. Artificial radiation is due to man-made events or procedures, such as nuclear energy leakage in accidents or nuclear weapon testing. This normally accounts for a small percentage of background radiation. This pie chart shows the breakdown of sources for background radiation. The largest natural source is radon gas from the ground, followed by internal sources like food and drink. Now, let's test your knowledge. Choose the appropriate words to fill in the gaps related to the discovery and detection of radioactivity and sources of background radiation. Radioactivity was first discovered by Henri Becquerel in 1896. Detection uses a Geiger tube connected to a counter or rate meter. Background radiation is mainly due to ionizing radiation such as radon gas. Half-life is the average time taken for half of the original mass of a radioactive sample to decay. The activity of a radioactive sample decreases over time. Half-lives vary greatly between isotopes. Uranium-238 has a half-life of 4.5 billion years, while helium-5's half-life is an incredibly short 1 × 10⁻20 seconds. Here is an example problem. Strontium-90 has a half-life of 29 years. If a sample contains 18.2 grams in 2012, we can calculate when the mass will fall to 0.15 grams. In question 1, a radioactive isotope has a half-life of 20 minutes, starting with 80 grams at 10 a.m. The time elapsed to 11 a.m. is 60 minutes, which is 3 half-lives, leaving 10 grams. Question 2 asks for the half-life of an isotope whose mass decreases from 24 grams to 6 grams over 60 days. This indicates that 2 half-lives occurred in 60 days. Since 2 half-lives occurred in 60 days, the half-life of the radioactive isotope is 30 days. The half-life of a radioactive source is also defined as the average time taken for the source's activity, or the number of nuclei to decrease to half its initial value. In example 2, source Z has a half-life of 3 hours, starting with an activity of 16,000 becquerels at 9 a.m. We want to find when the activity falls to 125 becquerels, which is 6 a.m. Example 3 involves isotope X, which decays to isotope Y with a 2-hour half-life. If there are 6,400 nuclei of X at 2 p.m., we can track the decay over time and find the number of isotope Y nuclei. Question 3 asks for the activity of a source with a 3-hour half-life at 2 p.m., starting with 600 becquerels at 8 a.m. Since 6 hours passed, the activity is halved twice, resulting in 150 becquerels. In question 1, substance P has a half-life of 15 minutes, starting with 1,280 nuclei at 9 a.m. The question asks for the remaining nuclei at 11 a.m. Question 4 asks for the remaining nuclei of hydrogen-3 after 48 years, starting with 8 billion nuclei and a half-life of 12 years. We need to calculate how many half-lives have passed. 48 years is equal to 4 half-lives. Therefore, the number of nuclei left is 1/2 multiplied by itself 4 times, then multiplied by 8 billion, which equals 500 million nuclei left. We can also find the half-life from a decay curve graph. By finding half of the initial nuclei number, we can read the corresponding time on the x-axis, which is the half-life. Question 1 asks to estimate the half-life from the given decay graph. Taking half of the initial activity, we find the half-life is approximately 20 seconds. Question 2 asks you to use the provided table of mass versus time to draw a graph and determine the substance's half-life. Based on the data, the half-life should be about 2 hours. Now let's complete the sentences. The half-life of a radioactive substance is the average time taken for half of the nuclei of the substance to decay. It is also equal to the average time taken for the activity of the substance to halve. The half-life of carbon-14 is about 5,600 years. If the current activity is 3,400 becquerels, it will fall to 1,700 becquerels in 5,600 years and 850 becquerels in 11,200 years. The number of nuclei would have decreased by 4 times.